Oh hey, welcome into the lab. We're going to be talking about the mole concept with Legos. But before we get in there, it's really important to remember your eye protective gear and your lab coat. What are we waiting for? Let's get in there.
Legos are actually pretty useful to understand really great concepts like the mole since they're super easy to visualize. The elements we are using today are hydrogen, helium, and beryllium. For clarity, we are going to have each brick labeled based on the number of studs and think of that as the atomic number. The listed data is for the actual element, not for the Legos themselves. We'll assume for all calculations that each Lego is the same individual weight, and we'll be using 5 sig figs for the true chemical elements, but for the Legos we'll be using 3 as it is as far as my mother's scales goes. Each of the 3 samples is 25 bricks. Visually, it is clear that the largest sample is the beryllium. Even though they are all the same number of things, that is because the weight. You can clearly see that individual items themselves are bigger, and it wouldn't make sense to compare 2 blocks of helium with 2 blocks of beryllium, saying that there's 2 of each, so they weigh the same. But when working with things like atoms and molecules, we can't go off of visual clues like we can with the Legos. So we have to mathematically prove our claim is correct. Before us, we have a zeroed out scale, and we are going to put in our sample and see what the whole weighs. Our sample is 40 grams. If we divide 40 by 25, we get brick is 1.60 grams. We can test the same thing with the helium. We get 20 grams, and 20 divided by 25 is 0.800 grams. So that means each brick is 0.800 grams individually. If we continue this trend with the hydrogen, then we will see, if we continue that with the hydrogen, we see that 11 grams divided by 25 equals 0.440 grams. So that is the weight of each individual brick. The reason we can compare these things is because we have a standardization. In this instance, the amount of bricks. So what the heck are you going to do if you're measuring with super duper duper small units like atoms or molecules or something of the such? Well, if we change our mindset and think of each group as one particular unit, then it kind of clears things up a little bit. But what unit do we use? Fortunately, we have a unit for that. It's called Avogadro's number, and that is 6.0221 times 10 to the 23rd, which is a lot bigger than 25 Legos, but I didn't have that many and I did not feel like finding it. So instead of thinking of them as 25 or 6.0221 times 10 to the 23, we just kind of give it a common name like mole. That way, it makes mathematics a lot easier. And I'm going to show you how it makes sense with a problem I have prepared for us today. And I know you're thinking, Catherine, that makes no sense. I have no idea what a mole of anything weighs. Fortunately, I have a solution for that as well. The periodic table. The periodic table has a super cool number on it that tells us exactly the weight of 1 mole. Now it happened to be the atomic mass, 4.0026 grams of helium in 1 mole of helium, which is super duper awesome if I want to plug it into, say, an equation. So if we were to ask what is the mass in grams of 3.7 moles of helium, we could do the calculation 3.71 moles of helium times 4.0026 grams of helium over 1 mole of helium equals 14.850 grams, or 1.4850 times 10 to the first grams, and we would get the proper answer for that equation.
In conclusion, thanks for coming to the lab today, and I hope that things couldn't be more clear.